here's the picture again, right? We're trying to find the work done lifting this half full tank of water all the way up the top. So that's our radius 2. This distance here is y. And I'm going to call this distance here x. And so I can see that x squared plus y squared equals 2 squared. So that x equals the square root of 4 minus y squared. And so that this length is then twice this. So the volume of this slice of water here is going to be twice x times 10 times dy, right? Because there's a small amount of dy thickness. And then the density is going to be, well, water is 1,000 kilograms per cubic meter times 9.8 meters per second squared. Right, that's the density of water. I don't want to write the units, but there's only so much space. And then the distance it's going to travel is going to be, well, this slice is going to travel the distance of y and then another 2 meters. Right, this length here is just 2. So it's going to travel y plus 2 meters. And we're going to replace this x with what x is equal to, which is the square root of 4 minus y squared. So that's what we're going to have to integrate from 0 to 2. Are there questions about this before we write the integral? I'm happy to address any questions. I can also show you a nicer picture if you want to see a nicer picture. Okay. So, sorry, yeah, come back, chat. And I feel like I'm not on my game today. There we go. Okay. I feel like I'm having a hard time using my computer. Anyway, we're going to be integrating this, and I'm going to use the other side of the board because, right, so setting these problems up is tricky. Integrating them can also be tricky. Go away, Adobe reminder. So we're going to be integrating, again, we're going to be integrating 2 times the square root of 4 minus y squared times 10 times dy times 1,000 times 9.8. That's a lot. So 2 times the square root of 4 minus y squared times dy times, I know the dy usually goes at the end, but whatever, times 1,000 times 9.8 times 2 minus y, 2 plus y, sorry, 5 plus 2, 5 plus 2. All right, so that's what we're integrating. We're integrating again from y equals 0 to y equals 2. Okay, so we're going to break it apart. I'm going to bring out the 1,000 and 9.8 equals 2. So that's going to be 9,800 times 2 is 19,600. And we go from 0 to 2 of, we've got 2 plus y times the square root of 4 minus y squared. Is going to be, so I'm going to distribute, I'm going to get 2 times the square root of 4 minus y squared. And then I'm also going to have the integral from 0 to 2 of y times the square root of 4 minus y squared. Now, the person who asked me the similar question makes sense. We also need brackets around that because we don't, that was a thing I want to say here. We just need to multiply everything. Are you missing a 10? I might be missing a 10. It is distinctly possible. I am missing a 10. Good call. Yeah, for the length, for sure. Times 10. Sorry about that. So let's just tack on a 0 there. It's easy to fix. So what I wanted to say is the person who asked me this question in the reflection or whatever, their tank was full. It wasn't half full. Why are the bounds from 0 to 2? Because, so we're imagining this is y equals 0, this is y equals 2, and the water lives from 0 to 2. Yeah, because it's half full. What I want to say is that if your tank was fully full, and your limits of integration were like from -2 to 2, then it becomes easier because this part just becomes 0 because that's an odd function. So if you're doing from -2 to 2, super easy. If you're doing from half full, from 0 to 2, or from whatever it's there, it's a little bit more challenging. But let's finish it off here. So this part here, well, that's half of a circle. Actually, it's a quarter of a circle, right? Because you know from 0 to 2, the square root of 4 minus y squared, the square root of 4 minus y squared looks like this. It's the right half of a circle of radius 2. And so if I'm integrating from 0 to 2, I'm getting that part right there. So this is going to be 2 times a quarter of pi r squared. This part here, we have to do a u substitution. We let u equal 4 minus y squared. Du is negative 2y dy. Negative 1/2 du is y dy. We have a y dy. So this part becomes red. Let's see, y dy, so I get a negative 1/2 integral y dy du, and then the square root of u. And my new limits of integration are, well, if y is 0, u is 4 minus 0. And if y is 2, u is 4 minus 4, which is 0. So this part becomes, and I would then change this to positive, and I would flip the limit of integration. This is going to be positive 1/2. Integrate this, it's going to be 2/3 u to the 3/2. And my limits of integration, since I changed the sign, I'm going to change the order and make it from 0 to 4. So that's going to be 1/3 times 4 to the 3/2, which is going to be 8. Just 8/3. So I get this number here, which is 2 pi, plus this number here, which is 8/3, all times 19,600. And yeah, I know things are kind of a mess here, but that is what we get. Yeah. I feel like I need to double check something real quick. Oh no, I'm good. Yeah, that's right. That's exactly right. So when you have these circular shapes that you've got, that you're either pumping fluid out of or finding fluid force on, oftentimes you get this kind of tricky circle thing happening where you're like, oh, I'm just finding the area of a circle. I'm not actually going to integrate that. And then sometimes you have other tricky things happening, like having to do a u substitution, or having to do having to say it's 0 because it's an odd function. So hopefully that wasn't too terrible. I know these problems get super messy. I try to keep them clean, but it is not always easy. If you want to look at a more nicely written version of that, here's a link to the document that I'm looking at. Grant draws some nice pictures, so I'd encourage you to scroll down to like the 3rd page if you want to see a better looking picture of that. But let me go ahead and look at, somebody asked, and I thought this was a good question. Oh, look at that. I think it was about question, I don't know if it was 41 or 42 on the section 6.5 about a tilted plate, which sounded kind of challenging. So let's try to find the fluid force due to pressure on a tilted plate. Also, I will say, there were questions. So if you have the cruel words today, just like not coming to me. So I posted quiz solutions. I would encourage everyone to take a look at them. If anyone wants to, I'm happy to go over any of the quiz problems, but I do feel like the quiz solutions I wrote are fairly easy to follow. I don't know, maybe I'm mistaken. But if you have questions about the quiz, I'm happy to address them here. I'm also happy to address them in office hours or via email or whatever. Let's go ahead and look at this problem 41 part C in section 6.5. Calculate the fluid force on one side of a 5.5 square plate. The plate is at the bottom of a pool filled with water to a depth of 8 feet and it's resting on a 5-foot edge and tilted 45 degrees. Okay, so here's the situation. There's the bottom of the pool. There's the top of the pool. That's 8 feet. And here is my 5-foot plate sitting on its edge at an angle of 45 degrees. And so, right, the plate goes like, so this is where my drawing skills are going to stop. The plate like goes back on me, so maybe I can try and draw it. Sorry, this is where I'm not a great drawer all the time. That looks dumb. Sorry, I'm trying to make this picture look great, and it just does not look great. Welcome to James's drawing class. Why can't I make this look the way I want it to look? It's because I'm trying to make it look too right. I think I've got it. Sorry. Maybe. Sure. We'll just do it stupidly like this. Fine. There we go. That looks okay, I think. So right, the plate is 5 feet long this way and 5 feet long this way. And sitting on the bottom of the pool, right, which maybe looks like that. Sitting on the bottom of the pool at an angle of 45 degrees to the pool. And so our question is, how much fluid force due to pressure is on this plate? And so really, this picture is not super helpful to me. What I really want is just this picture. At the bottom, I've got this segment here, which is 5 feet long, at an angle of 45 degrees, and it's 8 feet. Okay, and so I'm going to try to find how much fluid force due to pressure is on just a thin little strip. Okay. So what I really need to do, this problem, yeah, I feel like this problem is weird. So I feel like there's an arc length thing going on here. Does that sound right to any of you? That there's an arc length aspect to this problem, or am I just making stuff up? Okay, well here's what I'm thinking. Let's call this. All right, so I'm looking at like this little segment here. I want to know how much fluid force due to pressure is on that little segment. And we're going to think of that segment as being. See, this is where I'm having trouble. I'll fully admit. Am I going to call the length of that segment dy, even though it's at a diagonal, or am I going to have to call it ds? I don't know. I'm intrigued. What does the back of the book say? Good question. Let's see, section 6.6. Oh, which is the end of the back of the book here. That's interesting. My solutions end at section 6. My answers end in section 6.6. That's kind of funny. Oh, I have the answers to the even problems, not the odd problems. I guess that's not so helpful. All right, well, I'm supposed to work on our own. So, here's what I'm thinking. I'm thinking that we have this small segment here, and it's at a height of y. It's at a depth of 8 minus 1. That's a very good point. Thank you, Morgan. So we could definitely say that if I'm thinking of this having a height of dy, then yeah, the length of that part is exactly root 2 times dy. Because I'm going to call it dy. It might, let's see, actually, let's double check that. Yeah, no, it's longer. Yeah, it's root 2 dy. Sure. So then the force due to pressure is equal to the area times the depth times the, what's the other thing, times the density of water. Did it give us the density of water? No. I think this book uses 62.4 instead of 62.5. I don't know. All right. Yeah, no, I think you're definitely right, Morgan. Because if I'm looking at this small segment here, if that's 45 degrees, so I'm saying this is dy and this is, it's dx, but it's also equal to dy because they're the same. So it's 45, 45, 95. And this is definitely root 2 times dy. I think that's the right way to go. Okay, so yeah, so we got the area. Now, so the area is going to be the area of the strip, which is going to be, I believe, 5 times root 2 dy. The depth is going to be 8 minus 1. And the density is, I'm going to go with 62.5. So the other thing we have to do is now we have to integrate. So we're going to integrate this whole thing. So it's going to be, and I'm going to bring up the constants, because the constants don't just bring up. So it's going to be 5 times root 2 times 62.5 times the integral of 8 minus y dy. Okay, my lower limit of integration is clearly 0. What's my upper limit of integration going to be? How high does this thing go? It's not 5. Right? Because 5 is how long this thing is, because it's on its angle. So it's actually 5 over root 2. So that's how we would set that one up, unless I'm making some grievous error that is not occurring to me. And then the rest of that, I feel like the rest is pretty straightforward. And we integrate this, we'd have 5 root 2 times 62.5. The integral of this would be 8y minus y squared over 2 from 0 to 5 over root 2. And then we plug in, and we get 5 root 2 times 62.5. And then we get times 8 times 5 over root 2 is going to be 40 over root 2. And 5 over root 2 squared is 25 over 2 over another 2 is 25 over 4. It's not pretty, but it is what it is. Yeah. I really hate that saying it is what it is. Now it sounds like something the president said about a thing, whereas that's something I've been saying forever. It is what it is. Not going, I'm echoing that idiotic thing. Sorry. This is not a political class. It's just stick to the math. Just, you know, things are sort of interesting times we're living in. That's for sure. Yeah. Okay. So let's talk about, let's see. Some people have, those are okay. I don't want to spend too much time on all this, so let's, yeah. Sorry, it's always hard to figure out like what's the best thing to do with our time. So I want to show you guys some stuff about center of mass, because I will really admit this is something I've always had trouble saying the right way, but I feel like Grant's notes actually do a really good job of spelling it out. So I'm going to show you these notes. I'll also shoot you the link. This is a different page of notes. If you want to look at them yourself, you can. I'm going to share my screen here. I'm going to talk through this, and then we'll do an example or two. So, moments and center of mass. First, and I'm mostly going to read this to you also. So a little physics, right? Weight, also known as force, is mass times the acceleration of gravity. Where mass is, constant for an object, doesn't change. Acceleration of gravity can change with elevation, but whatever. So weight is force, mass is acceleration.
when a force is applied to a lever arm a certain distance from a fulcrum, a torque is produced, which causes the lever arm to rotate about the fulcrum. So, right, if you've got some fulcrum over here, right, can you guys see where I'm pointing at? Some length away from some force that is being applied to the lever arm with a length of d, then you're applying a torque, which is a force times a distance. So the greater the force, right, so I should say, if you apply the same force at a greater distance away from the fulcrum, you're exerting more torque because that lever arm has it's a mechanical advantage where it's giving you some advantage by doing this thing. And again, I feel like this is definitely a place where you might want to do some future exploring on your own because I'm not great in explaining this physical idea. It's just something that I don't always have the best words for. But the idea is that essentially the greater the force, the greater the distance, the greater the torque. Now moment, so torque, I feel like something we might kind of understand is something that we think about in vehicles, like we talk about like trucks having more torque, and it's all about this idea of being able to, apply force at a certain distance. Moment is a similar idea to torque. The only difference really is that instead of talking about force times distance to the fulcrum, you're actually talking about mass times distance to the fulcrum. So it's really kind of the same idea. You just don't have the force units, you have mass units. So you're not multiplying by gravity, essentially. So moment is mass times distance to fulcrum. In the metric system, that would be kilograms times distance. So kilograms times meters, for example, is a measure of moment, or the units moments are measured in. In the US system for mass is always awful. It's slugs. And really, I think of slugs as force or weight divided by gravity, which is kind of weird. So US system slugs. The center of mass is kind of like a balancing point. So if we look at this kind of thing here, this question asks, where should an opposing 10 kilogram mass be applied for the system to balance? So here's our fulcrum. Sorry, I feel like this question is, yeah, so we want the moment to, I'm like, where, so now I'm like, where is this supposed to be? I see. So, right, so we're trying to find a balancing point. Where should we pose it? Sorry, I feel like this question is confusing. So here's what we've got. I see. Okay, I get it. So here's our fulcrum, and we haven't drawn it, but there should be more out to the left here. And we're saying there's a 5 kilogram mass 1 meter from the fulcrum. There's a 3 kilogram mass 3 meters from the fulcrum, and there is a 2 kilogram mass 6 meters from the fulcrum. To balance that out, we're going to have to put a 10 kilogram mass somewhere over here. And so if we look at this, right, to balance this, we're going to have the torques or moments, right? They're not torques, they're moments. 5 kilograms times 1 plus 3 kilograms times 4 plus 2 kilograms times 10. Those are all the masses times distance. Those cause a clockwise rotation. And then this is going to have to be located at, I would say it would have to be negative 3.7 meters. Right, we need to be over here on this left side of this to balance those out. Maybe I'm missing something. Oh no, I see. I'm sorry. That question's a little bit. Yeah. Sorry. This question is saying something a little bit. System balance. I feel like that's not right. Sorry, I'm looking at these. I'm like, that seems like it's a little bit weird. I feel like this really needs to be at negative 3.7, right? We need to be negative 3.7 over here for the system to balance on this fulcrum here. That said, sorry. So again, my interpretation is not always excellent. We're talking about balancing. Basically, we're talking about the torque on one side, or sorry, the moment on one side balancing out the moment on the other side. And the only thing I really wanted to get to in these notes was that when we're trying to find the center of mass, or the centroid of the thin plate, the idea that I want you to kind of think of is that when you're trying to find the moment around either the y or the x-axis, you're kind of thinking about like the tendency of this object to swing around the axis, or as Grant has written here, think of the plate as a door attached to the y-axis. My, or the moment about the y-axis, measures the tendency for the door to swing about the axis, whereas mx measures the tendency to swing about the x-axis. So I often think about it as, let me stop sharing here. So I kind of think about it as my xy axis kind of lying flat, and I've got like some shape in the xy coordinate system, like maybe it's that same shape I was just looking at, kind of looks like this. Maybe I've got this shape living in the xy plane, and the moment around the y-axis is the tendency of this thing to swing either one way or the other. And if it's swinging down that way, it's got a positive moment, or I should say, if it's swinging kind of in a clockwise direction, right, it's got a positive moment. If it's swinging this other way, counterclockwise, it's got a negative moment. And the same kind of thing is true for the x. If we're talking about swinging on the x-axis, if it's swinging down that way, it's negative. Swinging down that way, it's positive. Okay. So, as much as it's good to have a good idea about kind of what these things, how these things work, in reality, you kind of just have to memorize the formulas. So let's talk about finding the moment in the center of mass for this thin plate. This plate that is bounded by the curves y equals the square root of x and y equals x, which looks like this. And these intersect each other at the point 0, 0 and at the point 1, 1. And I want to find the moment around the y-axis and the moment around the x-axis. Let's talk about the moment around the y-axis first. So the idea, like every time we do something with integrals, is that we're going to take a small representative strip and then try and find the moment for that strip and then integrate. So I look at this vertical strip here. This vertical strip, I'm going to think of as being at a distance of x from my y-axis. So the moment about the y-axis for just that strip is going to equal the lever arm length, which is just x, times the mass of that strip. The mass of that strip is the area of the rectangle times the density. We're just going to say the density is some constant delta. So it's the lever arm times the mass, where mass is going to equal just area times density. Okay. The area of this strip is the area of a rectangle, which is base times height. That's going to be the height, which is the top function minus the bottom function, square root of x minus x, times the base, which is just dx. So there's your area, and then we're going to tack on a delta for density. So some people do need to know how to find moments. Maybe not everybody. Someone asked me privately if they need to. I know that some classes are covering it. It might not be true for everyone. So I do feel like I should talk about it briefly because some people are covering it. But if this doesn't apply to you, it probably will eventually apply in 21C or D. But yeah, I would say not to stress too much about it. Obviously, it doesn't apply to you. Or your teacher might not have just gotten to it. But they probably just skipped it. But our coverage will be brief. So really the way I'm thinking about the moment around the y-axis is just lever arm times the area of this, and then the integrate. So the moment around the y-axis is going to be the integral from x equals 0 to x equals 1, because that's how far left around my rectangle scale. of x, the lever arm, or the distance to the strip, times the area of the strip, times this, I'm going to assume this density is constant. So that's how you find the moment around the y-axis here. We can calculate this. It's going to be density times the interval from 0 to 1. X times x to the 1/2 is x to the 3/2. X times x is x squared. We integrate. We get our density times x to the 3/2 integrated is x to the 5/2 times 2/5. This is going to be x cubed over 3 from 0 to 1. So we get 2/5 minus 1/3. Gosh, my notation today is really, really not excellent. And 2/5 minus 1/3 is, let's see, 6/15 minus 5/15 is 1/15. So we get delta times 1/15. So our moment around the y-axis is positive, which means we are likely to swing that way, to the right, not to the left. Okay. Or if you want to think, you're swinging like that way, right? You're going back that way in the first quadrant, not back that way in the second quadrant. Now here's the thing: the moment around the around the x-axis, depending on how you want to think about it, is a little more complicated or not. So yeah, and how do I want to say this? I want to say it in the least complicated way possible, really. Yeah. So there are two ways you can do. In fact, there are two ways you can do any of these. Kind of like with the, not exactly like, but kind of like with all the surface area stuff, how there was like a lot of different ways you can calculate, but you could always either do it with x's or with y's. The same is kind of true here. We could totally find the moment around the x-axis by thinking about the same sort of way. We could draw a horizontal strip. Say, okay, well, the distance from this horizontal strip to the x-axis is y. And so I'm just going to erase this part here. The moment around the x-axis is going to be the integral from y equals 0 to y equals 1 of the lever arm, which is y, times the area of our strip, or I should say the mass of our strip, which is going to be the length of it. So it's the right function minus the left function. The right function is x equals y. The left function is x equal to y squared. Times our density times the dy. This is the easy way to do it. So that's going to be density times the integral from 0 to 1 of y squared minus y cubed dy, which is going to be density times y cubed over 3 minus y to the 4th over 4 from 0 to 1, which is going to be 1/3 minus 1/4, which is going to be 1/12. So you get density times 1/12. Okay. There is another more terrible way of calculating this that I can show you if you want, but it's kind of not fun. It's fine. It's just you can calculate the moment around the x-axis in terms of x instead of doing it with an interval of y. Here's how you would do it. So here's what I'm thinking for moments. Whenever I'm thinking of trying to find a moment around an axis, I'm always thinking of distance to that axis, also known as the lever arm, times the area of the thing, or the mass of the thing I'm trying to move. So let's draw this again. And now here's where things are a little bit trickier. I'm looking at this thing here. If I do use a vertical strip, the problem with a vertical strip around the x-axis is that vertical strip isn't all the same distance from the x-axis. My lever arm is harder to calculate. What do? We pretend like it's all centered at the middle of the rectangle. So we say this distance here, that's going to be our lever arm. and that's going to be the average of the heights of the two functions. So here the lever arm is not equal to y. Well, I mean, it is a y value, but it's actually the average of the square root of x plus x. Well, I mean, it's the average of the square root of x and x. It's the square root of x plus x over 2. The distance, sorry, not the distance, the area of this thing is still the same. It's still the top minus the bottom times the dy. So that's your lever arm. Area of this strip is still the square root of x minus x times dx. And so then the integral to find the moment around the x-axis, again, I'm integrating my lever arm times my mass, which needs a delta. So it's going to be square root of x plus x over 2 times the square root of x minus x dx delta. This should be the same, right? We should be able to calculate the moment around an axis either way and get the same answer. Let's see. So when I multiply this out, I'm going to bring out the 1/2. Square root of x times square root of x is x. The middle terms cancel. Right? Square root of x times negative x and x times square root of x cancel out. And I get x minus x, so negative x squared. And that looks a lot like what I had before. Not really. You get delta over 2, integrate this as x squared over 2 minus x cubed over 3 from 0 to 1. So I get delta over 2 times 1/2 minus 1/3. 1/2 minus 1/3 is 1/6. 1/6 times 1/2 is 1/12. So I do get delta over 12. Just like I have over here. Okay. So if you can do things in terms of the variable that's easy to say, oh, I'm just y away from the axis or I'm just x away from the axis, I encourage you to do it that way. But this other formula is also a thing that's kind of terrible. I do also want to say that this allows us to find the center of mass. So to find the center of mass, and let's see, yeah. Sure. So there's kind of 3 things we need to know about this sort of stuff. We need to find the moments, my, and mx, and then we need to find the center of mass. So the center of mass is essentially where this thing would bounce. So there's some x value where if you had like a vertical line of x value, it would balance on the other side. Or the moment, another way of saying is the moment around that line would be 0 because it doesn't want to swing either way. In the same way, we can find a y line where the moment around that line is 0. That's the center of mass line. So the center of mass, we call those coordinates x bar, y bar. And the x coordinate is equal to the moment around the y-axis divided by the total mass. Right? It makes sense that the x coordinate is talking about the likelihood to swing around the y-axis. And similarly, the y coordinate of the center of mass is the x moment divided by the total mass. We already know what the moments are. We need to find the mass. The mass is easy. The mass is just the area times the density. So it's the integral from 0 to 1 of square root of x minus x dx times the density. I'm going to erase this because we already did. Except for that. So the total mass is density times integral of this is x to the 3/2 times 2/3 minus the integral of this is x squared over 2, 0 to 1. So we're getting 2/3 minus 1/2, which is 4/6 minus 3/6, which is 1/6. So we get delta over 6. So then our coordinates for x bar are going to be, well, x bar is going to be my, which is this. So it's delta over 15 over delta over 6. The deltas will cancel. And then for the second coordinate, it's mx, which was this thing, delta over 12. over delta over 6. Simplifying that, we get 6 over 15 comma 6 over 12, which reduces to 2/5 comma 1/2. So the center of mass is not quite halfway over, but exactly halfway up, which is kind of interesting. Yeah, not quite halfway over, maybe like right there-ish. The center of mass does not have to be inside the area, depending on the shape. Okay. So the last thing I want, so kind of feel like I should do more examples, but the examples just get to be so tedious. So here's what I'll say about this center of mass moment stuff. So in general, if you've got some shape, some region, maybe it looks like this, where this bottom function is y equal to f of x, or x equal to g of y. And the top function is, x equal, I'm going to call them the same name, x equal to f of y. That's bad notation. Fine. I'll come back to that. Or y equal to g of x here. Except usually we call the top function f and the bottom function g. Sorry. Jeez. What a day. Okay. So if I want to find the moments here, the moment around the x-axis, that's the one I don't want to do first. The moment around the y-axis is the easy one. I'm using a vertical strip. And I'm thinking, okay, the moment around the y-axis is the integral from whatever this value is. So let's call this point AC. Let's call this point BD. The moment around the y-axis is the lever arm, which is x, times the area of this times the density, which is going to be the top function minus the bottom function. From A to D. And then the moment around the x-axis is the more complicated one. It's going to be, from A to B, not A to D. It's going to be the lever arm, which is the distance that's halfway between the top and the bottom function. That's going to be the average of f and g. So f of x plus g of x over 2 times, again, the area of that, which is f of x minus g of x dx. And of course, I forgot the deltas. Deltas for density. People usually rewrite this though, because this does simplify a little bit. This is equal to, I'm going to bring out the 1/2, delta over 2, integral from A to B. When you multiply f plus g times f minus g, you get f squared minus g squared. So that's what those formulas look like for the moments around the y-axis and the x-axis in terms of x. And then the total mass is just the integral from A to B of f of x minus g of x. And then finally, the center of mass is the y moment over the mass and the x moment over the mass. And I mean, they're kind of gross. They're kind of just formulas you should memorize. Their formulas become much easier when you take them to class where you see them again after you've done double integration. There was something to say here. Yeah, there's not a lot more to say. Oh, the other thing I want to say is, so if you do them in terms of y, so like if we solve this for y, and so like x equals, I'm going to call it something else, like h of y. And over here, this function is x equal to k of y. Then you can write the moment around the x-axis very easily. The moment around the x-axis is going to be the integral from c to d of y times the area of my horizontal strip, which would be h of y minus k of y, dy. And then you could also do a terrible one like this, right? Where it's your, so then basically the nice equation and the terrible equation switch places. So if you're going around if you're doing in terms of x, my is nice. It's your nice lever arm times your function difference in functions, and your moment around the x is terrible. If you're doing the moment around the y, or if you're doing things in terms of y, the moment around the x-axis is nice, and the moment around the y-axis is the one that's terrible. That looks like this. It's delta integral from c to d of your right function squared minus your left function squared. So I don't have a problem like that off the top of my head, Morgan. Let me see if there's one in the book. So I suppose we could ask a question. So I guess I can make one up. So let's make one up. And I feel like it shouldn't matter if the thing goes through it or not. So let's say our region is, I'll make something not too terrible. So let's say, yeah, I'm just gonna, so the region is bounded by y equal root x, x equal to 4, and y equal to 0. So here's our region. And I want to find the moment around, do you want me to pick a horizontal line or a vertical line? And do you want it to go through the thing or not? Like I'm thinking maybe, what's the moment around the line x equals 3? X equals 3 seems like it might turn out to be terrible, but let's find out. Sure, and x equals 5. I definitely expect the one about x equals 5 to be negative. So here's what I'm thinking, right? I'm thinking that the moment, which I'm just going to write as the moment because it's not around the x or the y axis specifically. The moment around the line, let's do 3 first. So again, I am drawing a vertical strip. It's always going to be easiest if your strip is parallel to your axis of momenting. So what's the lever arm? Well, I'm thinking of the strip as being located at x. So the length of the lever arm is x minus 3. That's how long my lever arm is. And right, if your lever arm, if your stuff is to the left, your lever arm gets counted as negative, which is fine. And then it's going to be the top minus the bottom. So it's going to be root x minus 0 dx. From 0 to 4, there's my density out there. So that's how it's the moment around the line x equals 3. Which is different than the moment around x equals 0, right? So I should say, the moment around 0 should be way bigger because there's a lot more of this to the right of 0 and there's a lot more tendency to swing down that way. The moment around x equals 3, I'm guessing is probably going to be negative because I'm betting it's more likely to swing that way than it is to swing that way. Let's find out. This is going to be, okay. So it's going to be delta times the integral from 0 to 4 of x times root x is x to the 3 halves minus 3x to the 1 half dx. So we integrate, we get 2/5 x to the 3 halves, 5 halves minus 3 times 3 halves, sorry, 3 times 2/3 is 2, x to the 3 halves, yeah, from 0 to 4. And plugging it in, we get delta times 4 to the 5 halves is 32, so we get 64 over 5. And 4 to the 3 halves is 8
times 2 is 16. And 16 is 80 over 5. So we get 64 minus 80 is, yeah, we get delta times negative 16 over 5. So here we do get a negative moment because of how this is set up. Because there's more of a tendency to swing that way than there is to swing that way, which I know is super helpful when I do it like that. Now, so what is it? Well, so a negative moment means just what I was saying, right? So basically, the negative moment, if you're talking about a moment around the vertical line, it means you're likely to swing to the left down to that vertical line instead of to the right. Right? I'm thinking of like a piece of paper on, and here's we should have like a nice vertical. This piece of paper is kind of, let me get a better piece of paper. Or how about this? Yeah. So I'm thinking about like, this is my region, and I'm asking, okay, here's this line that's cutting my region, right? Like this, right? Like, and what's the likelihood of my region to swing this way or that way? Well, if we're swinging left, we're calling that a negative moment. And if we're swinging right, we're calling that a positive moment. And in this case, right, there's so much more on this side that it is likely to swing this way, and we're going to have a negative moment. The same thing is true for around the x-axis. So if you're around the x-axis, a positive moment means you're swinging up into the first quadrant like that. A negative moment means you're swinging down into the fourth quadrant like this. Hopefully that helps kind of spell it out. I would encourage you to look maybe for some YouTube videos about this, because I do think there are people that explain it much better than I do, and kind of can talk more about the physicality of it. Anyway, if I was trying to find the moment around x equals 5, now this is where I think I'm not sure. I'm pretty sure it's just going to be x minus 5. Because the lever arm should be negative. And so, yeah, so I don't think we need to do that problem, even though I know someone asked me to. But right, it would just be, the only difference would be instead of a 3 here, you'd have a 5 here. So instead of a 2 here, you'd have, well, let's see, you'd have 5 times 2/3, so you'd have 10/3. And so over here, when you plug in, you'd have 8 times 10/3, which is 80/3. And so then you would have 64, right? So it'd be more negative, which makes sense. But it's not going to be 5 minus x. It's actually going to be x minus 5. I know I wanted to do 5 minus x as well, because that seems like the right thing to do to me, but it is not. It's going to be x minus 5, because it should end up being a negative value. All right. Yeah. I think we've talked, well, we probably haven't really talked enough about moments, but I think I've talked enough about moments for today. That's it. If you have more questions about them, I really am happy to talk about them in office hours or on email, but it's just kind of, here's a formula, throw things at the formula. Let's talk about moving into section 7.1, which is a lot of kind of bizarre integrals, like the following. And I don't know, bizarre is quite the right word, but oh, darn it. Of course, I timed out. Let's see if I can reload this here. Okay. Okay, let's see. Sorry, one sec. So, looking at your textbook for just 1 second here, it does seem interesting that they define the logarithm to be this integral. Gosh, yeah, this section is, I feel like this book feels way more all over the place than I remember it being. Then this section, they talk about all these other things. So yeah, all right, well, here we go. So they define the natural log of x to equal the integral from 1 to t of 1 over x dt. dx, sorry. I think I got that backwards. 1 to x, 1 over t dt.
which I don't think is super duper important to know. It feels kind of weird to do this, but it is true. Right? If we integrate 1 over t, we get the natural log of t, and then natural log of x minus natural log of 1 is natural log of x minus 0. So it works, but it's just kind of strange. Yeah, I just feel like, sorry, I feel like I'm all over the place, and I apologize for not being totally all there today. But let's look. So I would say a lot of the section looks like it's a lot of U substitution stuff. So for example, I'm seeing questions in the homework like things that look kind of super bizarre, like the integral of 3 natural log of x over x times the natural log of x dx. I'm sure whoever thought of this problem thought they were very clever, because it's a relatively straightforward U substitution if you know what to look for. So we're back in U substitution land, where we're looking for things to call U so that their derivative is also showing up. So I could pick U equal to the natural log of x. But, well, in fact, I don't actually know if that's the right choice or not. I know a better choice, but let's try U equal to natural log of x. What's the derivative? Oh, it's 1 over x. Do I have a 1 over x dx? I do. Here's my 1 over x dx. So this is 3 natural log of x over natural log of x times 1 over x dx. And again, right, I'm always making the choice to deal with the du dx stuff first. So then I can say that this is the integral of 3. Now be careful, it's not u, it's the natural log of u over u. And then we have to do a U substitution again, which is never fun. But we could let, we want to use a different letter. We could let w equal the natural log of u, and then dw is 1 over u du. So this integral is exactly going to become the integral of 3 du over u is dw, and natural log of u is w. And then we have to go back and say, okay, the integral of this is 3 halves w squared plus c. And then we plug back in what w is, so it's 3 halves natural log of u squared plus c. And then we plug back in what u is, which is 3 halves natural log of x squared plus c. But I think there's a better way to do this. So this isn't wrong. This is totally right, totally correct. I would do it this way. But sometimes you can see a better choice for you. So here's a better choice for you. The natural log of the natural log of x. The derivative of the natural log of x is, well, the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is 1 over x dx. Oh, look. Oh, look. That's exactly that. So I could rewrite this integral as the integral of, well, the stuff circled in red is taken care of. That's my du. And then I'm left with 3u on top. That's going to be 3u squared over 2. And then I can plus z. And I can plug back in u equal to the natural log of x and get 3 halves times u squared, which is the natural log of x squared plus c. So sometimes there are better U substitution choices to make than others. Let's see. And then so I do feel like I should talk about for a second in this in this section. There are some other things as well. Yeah, I feel like, sorry, I'm just looking at this chapter. I'm like, they just do some weird stuff here. So they do talk about the integrals of tangent, cotangent, secant, and cosecant, which I suppose is something we should mention. Yeah. So these are also done with the U substitution. What's the integral of tangent of x? Well, it's the integral of sine x over cosine of x. And then I can do a U sub. I can say, oh, U is equal to cosine. Oh, wait, why wouldn't I pick sine? I could say U is equal to sine, which seems like a better choice, maybe. No. Du is equal to cosine of x dx. The reason we don't pick sine is because I don't have cosine of x times dx. I have 1 over cosine of x times dx. So this doesn't work. We have to pick u equal to cosine of x. So that du is negative sine of x dx. So that negative du is positive sine of x dx. And then we can rewrite this as sine x dx is negative du, cosine is u. I might rewrite this as negative integral of 1 over u du. But we know the integral of 1 over u is the natural log of u, or really the absolute value of u. So it's the negative natural log of the absolute value of u, plus c, which is the negative natural log of the absolute value of cosine of x, plus c. So the integral of tangent is the negative natural log of the absolute value of cosine of x. Or, because people like to write it a different way, I can bring this -1 coefficient up as the power, and cosine of x to the -1 power is the reciprocal of cosine, which is secant. So some people prefer to write this as positive natural log of the absolute value of secant of x. Which I say either way is fine. I would encourage all of you to find the integral of cotangent on your own the same way. Cotangent's even slightly nicer. They're all in your book in this section 7.1, by the way. But I should point out the integral of secant and cosecant because they're kind of tricky. And they actually really, so I'll say something about this. So I want to find the integral of secant. I want to use a different color pen. So how do I do this? Well, the real answer is so the integral of secant is actually kind of interesting. Look it up sometime if you have a moment. It actually has to do with the making maps. If you've ever noticed people talk about how like the Mercator projection map, and you know how like the latitude lines get further and further apart as you go up. Well, the length of those distances between latitude lines actually has a lot to do with the integral of secant and the way that you project a circular spherical thing onto a flat thing. Pretty cool, kind of neat. Long story short, people cared about this integral. Like it was something that they actually wanted to find. And so they did. I can't explain to you how they did it right at this moment because we don't have the mathematical tools to do that yet. We will after we learn about partial fractions. For now, though, I will just say that the way that people integrated it, they found the answer, and they're like, oh, there's this other slick way we can do it now that we know that the answer is the following. So people know that the answer is the natural log of the absolute value of secant of x plus tangent of x plus c. And when you take the derivative of this, it doesn't immediately speak to that, right? The derivative of this is 1 over secant plus tangent times the derivative of secant plus tangent, which is secant tangent plus secant squared, which is exactly secant times secant plus tangent in quantity. So the trick here that they learned to do after they figured out what the integral was to multiply the top and the bottom by secant plus tangent. So check this out. I'm going to multiply the top by, I'm actually going to write it out of order. I'm going to do the top as tangent plus secant
we do the bottom as secant plus tangent. So that when I rewrite it, when I multiply out the top, I get secant x tangent x plus secant times secant is secant squared x over secant tangent, secant plus tangent. But look, the top is exactly the derivative of the bottom. So I can say, oh, I'm going to do a u substitution. I'm going to let u equal secant x plus tangent x. That's the denominator. And then du is going to be the derivative of this, which is, well, the derivative of secant is secant x tangent x. The derivative of tangent is secant squared x dx. That's exactly what's on top here. So this becomes very, very conveniently the integral of du over u. The integral of du over u is the natural log of the absolute value of u plus c, which is the natural log of secant x plus tangent x. So these integrals you definitely want to memorize all the trig functions. So you should know, now at this point, you should know all the integrals of trig functions: sine, cosine, tangent, cotangent, secant, cosecant. They are in the book. I do recommend memorizing them. And then I guess the last thing I should say in this section, which I thought we had talked about, but maybe I'm conflating things, is the they're talking about derivatives here. What? Okay, we don't care about u. Sorry, I'm trying to like go through the section and see. Okay, sure. So they were talking about also in the section how like the integral. We know the integral of e to the x is e to the x. What about the integral of 2 to the x? I feel like we've talked about this already. I'm pretty confident I said something about this before. The integral of 2 to the x is just 2 to the x divided by the natural log of 2 plus c. And the reason for that is because the derivative of 2 to the x makes you multiply by a natural log of 2. So we know that the derivative of 2 to the x is 2 to the x times the natural log of 2. So if I divide both sides by the constant natural log of 2, I can say, okay, the derivative of 2 to the x over natural log of 2 is equal to 2 to the x. But saying the derivative of this is equal to that is exactly the same as saying the antiderivative of that is equal to this. The antiderivative of that is equal to this.